Alright, so we talked about last time about how to set up electron configuration writing, and today I'm going to teach you how to do it with part 6 here. The first thing you have to remember is you always start at the X, and whatever the white line goes through, you write whatever is in red. Now how do you know when to stop? Well, you stop when all the electrons have been accounted for. So let's do lithium. So we're going to write lithium's symbol, which is Li. And we see it's got an atomic number of 3, and its atomic mass is 6.94. Round that to the nearest whole number, so 7. Now, how many electrons does lithium have? Well, lithium has 3 electrons. I know that because the atomic number and the electron number are always the same in something that's neutral. So I go up here, and I have to account for 3 electrons. Well, what do I go through first? I go through 1s. Electron configuration is very repetitive because you're always writing the same thing. It's just a little longer if it's a bigger element. And then up here, on the exponent where the s is, I'm going to put the number of electrons that will fill that s sublevel. Earlier we talked about the different sublevels have different maximums they'll take. S was 2. So the first thing that we're going to do is put 2 of those 3 electrons in the s sublevel. And why we're going to fill it up completely? Well, that's what the alphabet sequence says. You're not going to put 1 electron in there. You're going to fill it up completely before you move on to the next one. So as you're going along here, you're thinking, all right, I've accounted for 2 of the 3, so I have 1 more to go. And where do we go after we get to the end of this diagonal? Well, we go up to the top of the next one. And what does it go through? It goes through the 2s sublevel. So I write 2s. And how many electrons will fill the s sublevel? Well, 2 will. But how many electrons are left? Only 1. So I'm going to put a 1 there. Now your exponents should add up to your z value, or your electron value. So 1 plus 2 gives me 3. And there is your electron configuration for lithium. Pretty straightforward. Well, what if we were to try nitrogen? So I'm going to write the symbol for nitrogen, N, and I see that it's got a mass number of 14, and it has an atomic number of 7. And how many total electrons does it have? Well, it has 7, so I got to count for 7 electrons in nitrogen. Always start right here. Goes through 1s, so I write 1s. And that's 7 of the... So how many will an s hold? S holds 2. So I'm going to fill those up there. And as I'm going along, again, you can do this in your head. That's 5 left. So what do I do next? Well, it comes after 1s. Well, we get to the end of the arrow here, we go up to here. 2s. So I write 2s. 2s. How many will an s hold? It'll hold 2, so I put 2 in there. Now how many are left? 3 are left. What do I do after 2s? Where do I go? Well, after 2s, we go to what? Well, what does the next diagonal go through? It goes through 2p. So I write 2p. How many electrons will the p hold? Well, it will hold 6. Do I have less than 6? I do. I have 3. So I can put all 3 right there. And there is your electron configuration for nitrogen. Do the exponents add up to 7? I think they do. 3, 2, and 2. That gives me 7. There's your electron configuration for nitrogen. So it's really straightforward. It's really repetitive. And the only reason it would get hard is if you have to go way down here. But that's the whole point of learning this pattern, is you know the order of increasing energy. And this is the map that you follow to figure out what the next highest energy sublevel is. And it's always going to follow this pattern. There are some exceptions to the rule, but we really don't get into those into this course. That's how you take care of electron configurations. So let's move on to the next slide. Trying to keep the pattern on the screen. All right. Okay. So this is just kind of a review with some of the stuff done for you already. These are called box diagrams, and what they are supposed to show you is, as you can see on the y-axis here, that increasing energy. Well, if you notice the pattern here, the higher it is, the higher the energy. Well, look at the pattern: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p. Well, that's the same order that we have: 1s, 2s, 2p, 3s, 3p, 4s, 3d. You'll notice that, and then 4p also. So this is the electron configuration for hydrogen. It only has one electron, so we put the 1 there above the s. It would be the simplest of all of your electron configurations. And sometimes we write the box to represent the orientation, the orbital. Well, an only has one orientation, so we only write one box. P has 3 orientations. That's why we write 3 boxes. D has 5 orientations, and that's why we write 5 boxes. If there was an F up there, they'd have 7 boxes. And each little box can hold 2 arrows. And each arrow represents an electron. And traditionally, we always put the first arrow up. If there's a second arrow in the box, then we would write that as a down arrow. So let's say that there's this, oops. Let's say that there was a second let's say there was a second arrow. It would go, whoa, it wouldn't go like that. It would be a little too big. It would be something like that, if it was helium that we were drawing. Okay, so this is just another way to represent configurations. It just shows the electrons separated out. And again, the reason the boxes are beveled or separated like this is because they're supposed to be showing you higher energy levels. We already talked about how you have to fill up the orbital completely. We know that helium would be 1s2. The 2 there is because it has 2 electrons. And the 1s has to fill up completely. So we put the arrow going up, arrow going down, and this is your electron configuration for helium up here. This is the box diagram down here. Notice all these boxes are filled. If I was asking you to draw the box diagram for helium, I wouldn't expect you to put all these empty ones. It's just showing you that there are others other than the ones that you have to draw. That should look familiar. There's lithium's configuration. We didn't do beryllium's, but it would be 1s2, 2s2. Boron has a total of 5 electrons. 2 plus 2 plus 1 gives you 5. You'll notice that I didn't put these symbols that I taught you earlier. I would want you to do the symbols if we were doing this on paper. But you'll notice that these arrows down here represent the exponent. So there's your 2 1s electrons. There's your 2 2s electrons. And then you see there's 1 electron in the 2p. That's why we have 1 arrow pointing up in this one. Now, Hund's rule. You'll notice that for carbon, which has 6 electrons, we fill up our 1s, then we fill up our 2s, and that's 4 out of the 6 electrons. So there's 2 extra electrons. Well, we know they go in the 2p. I can see that by the electron configuration. But how do I fill them up here? Well, the electrons will not pair unless they're forced to. Okay, think of the electrons getting into separate rooms, and each room will only hold 2 electrons. If the electrons are going to get in there and they can't stand each other, they're going to get into separate rooms. You just think of it like negatively charged. Things that are negative repel other negative things. That's what we're talking about here. So instead of putting an arrow here, if I was to put an arrow here, like that, instead of this, that would be wrong because I'm breaking Hund's rule. These electrons have paired up when there's still room for the other electrons to go. Okay, so that's why we put them here separately. And if there was a third one, then I would put it here. The only way I would put pairs is if there was a fourth one in the P and I had to fill it up there. And there would be the rest of your electron configurations for the second row, or the second period of the periodic table. You can add up the exponents and tell. 3 plus 2 is 5, plus 2 is 7, there's nitrogen. 4 plus 2 is 6, 6 plus 2 is 8, there's oxygens. Fluorine is 9, and neon is 10. Alright, that's part 6. We'll continue with part 7 later on.